Hello everyone, my name is Sean John. I'm currently a second-year PhD student at Yale University. Welcome to our presentation on learning spatial-temporal correspondences of cardiac motion from biomechanics-informed modeling. This is a joint work with Chen Yu, Sean An, Juntang Zhuang, Professor Lawrence Stabe, and Professor James Duncan. Learning spatial-temporal correspondences characterized by displacement vector fields from medical images is important to understand the underlying dynamics of anatomical structures. The DVF is especially important for cardiac motion, whose functional assessment is often analyzed using CNMRI or echocardiography. Specifically, accurate prediction of the DVFs across cardiac sequences enables regional myocardial strength estimation, which contributes to the localization of myocardial infarction. A wide range of deformable image registration methods have been studied for medical images to obtain reliable DVF measurement. Regularization is often imposed to ensure smoothness along with a dissimilarity measure. Such methods include B-splines, which use the bending energy of a thin plate metal, and optical flow, which uses total variation. For cardiac motion estimation, incompressibility of the myocardium is also used to incorporate physiology-inspired prior into the registration process by enforcing, for example, a divergence-free constraint. However, geometric properties in other structures, such as the right ventricle, is not guaranteed. Myocardial segmentation is also usually required to apply such constraint. With the advent of deep learning, convolution neural networks have been widely applied to unsupervised learning of deformable registration. Diffeomorphic constraints and L2 norms on displacement gradient are usually used for regularization. However, biomechanical plausibility is usually not explicitly considered, and thus estimated displacement field might result in unrealistic motion. To encourage physical plausible transformation, pre-trained variation autoencoders can be used as regularizers in the registration pipeline to enforce implicit constraint to the DVF. However, such regularizers are often trained separately on manually generated datasets, which require physical simulations and thus can be time-consuming and complicated. Due to the intra-intervariability in clinical datasets, such network-based regularizers might also be biased when evaluating new datasets. In this work, we propose a biomechanics-informed regularization explicitly as a prior for DVF estimation to better preserve geometric properties without requiring myocardial segmentation. Using a separate network as regularizer might introduce additional steps and thus increase complexity and computation. By contrast, our proposed methods show advantages in generalization when applying to new datasets. The consistency across different cardiac structures is also improved in our proposed methods due to the more generic assumption. We validate our methods on 2 public datasets and conduct extensive experiments to show its effectiveness and robustness over other competing regularization techniques. The proposed framework is illustrated in the above figure. We utilized an explicit biomechanical regularization on the estimated displacement vector field from the U-net-shaped registration network, which takes pairs of moving and fixed images as inputs and outputs the estimated DVF. We describe the details of biomechanics-informed modeling and the derivation for our proposed loss functions in the following slides. From the classical definition of the strain tensor in the infinitesimal linear elasticity model for 2D displacement, we have the strain expression as a function of the deformation gradient. We then define the linear isotropic elastic strain energy density function for each pixel as follows, where C here is the stiffness matrix describing material properties of the deforming body. EP is defined to stiffness and νp as Poisson ratio. In this paper, we treat EP as constant and νp as hyperparameter. The prior probability density function of the DVF can be written in a Gibbs form. The optimal DVF you had optimal can be obtained through a maximum a posteriori optimization. We assume the noise between ground truth measurement U and the DVF estimate U hat is normally distributed with zero mean and sigma square variance. As the ground truth measurement U is hard to acquire, we utilize the image dissimilarity between the transform image IM worked by U hat and the reference image IF to evaluate the difference of U hat with the ground truth motion field. From the prior PDF of the DVF in equation 4, our proposed method can be written as in the following, where n here is the number of samples. We apply L2 norm for the image after computing the strain energy density with scalar value entry for each pixel to penalize unrealistic motion. When segmentation masks are available for certain cardiac structures for an input pair, we can further improve the approximated difference of U hat with ground truth previously computed using image dissimilarity by adding an auxiliary segmentation loss term, where SFIJ denotes the segmentation mask of cardiac structure J for image pair with sample index I, and K here is the number of cardiac structures. We validate the effectiveness of our proposed methods on the public available ACDC 2017 dataset. It contains 100 patients including the full 5 categories with even split: healthy, previous myocardial infarction, dilated cardiomyopathy, hypertrophic cardiomyopathy, and a normal right ventricle. Segmentation labels of left ventricle, RV, epicardia, and boundaries for end-diastolic and end-systolic frames are given in the dataset. For this data, we use 60 patients for training, 20 for validation, and 20 for testing after a random shuffle. We also validate our method on another public available LV quantification dataset from 2019. It contains 56 subjects and includes 20 frames of the entire cardiac cycle. Segmentation labels of the endocardium and epicardium boundaries are given for each frame in the cycle. In this paper, 34 patients are used for training, 11 for validation, and 11 for testing after a random shuffle. We set the ED frame as the moving image and the ES frame as the fixed image in the ACDC and LV quantification datasets in order to estimate cardiac contraction. Each slice in both datasets is cropped to 96 by 96 with respect to the myocardial centroid after min-max normalization. We compare our proposed framework with several state-of-the-art registration methods, including B-spline, implemented using simple elastics, optical flow, implemented using Scikit image registration package, a learning-based registration framework using VAE regularization, and another learning-based registration framework using L2 regularization. The learning-based registration algorithms are implemented using PyTorch with Atom Optimizer on 100 epochs. The learning-based model run 18 to 30 minutes on a single NVIDIA GTX 2080 Ti GPU with 12 GB memory for training and validation. We choose SNOOPy equals to 0.4, lambda equals to 0.05, and gamma equals to 0.01 for auxiliary segmentation loss in our proposed methods after optimizing hyperparameters. To evaluate our proposed methods, we compute dice coefficient, J-curve index, Hausdorff distance, and average symmetric surface distance to evaluate segmentation conformance. We also compute Jacobian determinant to evaluate the quality of the generated DVF. Due to the time limit, we only show our results on the ACDC dataset in this presentation. Visual assessment of our proposed methods compared to others is shown in the above figure, where we can see that B-splines in optical flow generate artifacts in the myocardium, especially in the highlighted blue patch shown in the third row. The RegNet plus VAE creates unrealistic motion in the right ventricle region, especially in the highlighted green patch shown in the last row, which might be due to the penalization of the VAE regularizer mainly focusing on the myocardium only. Our proposed methods in the last two columns show improved motion compared to RegNet plus L2 with smoother and more biomechanic plausible motion. A quantitative assessment of our proposed methods is reported in the table. Our proposed methods outperform others in the cardiac structures including LV and epicardium across all evaluation metrics. Our methods yield higher performance in terms of DC and JD in right ventricle and similar performance with B-spline and optical flow in terms of HD and ASD. From the Jacobian determinant evaluation, our methods outperform others by having a closer value to 1, showing that the volume remains constant after the transformation. In this paper, we propose a data-driven approach for cardiac motion estimation with a novel biomechanics-informed modeling and regularization laws. Our proposed methods generate more biomechanical plausible DVFs for all cardiac structures in the image without requiring myocardium segmentation or introducing additional steps compared to network-based regularizers. Our proposed methods outperform other state-of-the-art methods on both AC/DC dataset and LV quantification dataset using quantitative evaluation matrix. Future work will validate current work on other modalities such as TACT and MRI and show its effectiveness in more standardized 3D clinical datasets with additional matrix to assess local abnormalities. Please check out our poster and paper for more details of our work. Thanks very much for listening. I will be very happy to take any questions.